right, time for another video presentation. Today we are going to follow up with our conversation of work and power and relate that to energy. And in particular, for our purposes, it's what we call mechanical energy. So first off, work and energy are related. Energy is the ability to do work. So if I'm going to do 1,000 joules worth of work, I will need 1,000 joules worth of energy. And that's a way of telling you that the unit for work and joules, work and energy are the same. The joule is the unit there. Okay, so the unit will be the same. We're off to a start here. Now, you're probably familiar with some of this stuff already. Mechanical energy, there's two types of energy. And the first one we're going to talk about is kinetic energy. And kinetic energy is going to be the energy of motion. Something has energy just because it's moving. And you know that something moving can do some work. That's why you get out of the way if something is moving at you, because you know it can do some work on you. Kinetic energy, we'll use the symbol Ke here, is equal to 1/2 the mass multiplied by the speed squared. So we're familiar with mass and we're familiar with speed, and we're now relating that to kinetic energy. So here's a very introductory problem about kinetic energy. So why don't you give this one a try, and when you come back, I'll give you the answer and show you my solution. All right, welcome back. The answer I got was 250 joules. Is that what you got? Well, here's my work for it. As usual, we identify the information. There's my mass and my speed. I'm looking for the kinetic energy, and here is the formula. So I'm plugging in my variables. Here I've taken the 1/2 of the 20 to get the 10. 5 squared is 25. And then so I came up with 250 joules. How did you do? All right, well, the other type of energy, I mentioned there will be two types of energy, two types of mechanical energy that we'll talk about. So the other one is going to be potential energy, stored energy. Lots of different kinds of potential energy. I guess gasoline, before you start to ignite it and get it to move your car down the road, could be considered a form of potential energy. But we're going to talk about a particular type of energy, potential energy, and that is what they call gravitational potential energy. The potential energy due to the position of an object. So there's the ability to do work if you are a certain amount of height above the ground, and you know that if you drop something heavy on you, it can do some work on your foot, let's say, if you dropped it on your foot. So gravitational potential energy is, like I said, the energy that an object has because of its position. Okay, so it should make some sense here that the gravitational potential energy is mgh. Because if you think about it, the amount of work you would do in lifting something, remember, is the weight of the object, that's the mg, multiplied by the height. Now, we used distance before when we talked about work. Height and distance are going to be interchangeable here, but in particular, the height is the distance off the ground, the vertical distance off the ground. Okay, so let's see how this works out. Here's a problem, and an introductory potential energy problem. So let's see how you do on this one. When you come back, I'll give you my answer, and I'll show you my work. All right, welcome back. How did that work out for you? Okay, so let's see what we got here for the potential energy. I got 2,450 joules. Is that what you got? Well, let me explain my thought process to you. Here is my information, that's the first step of every problem. And then I am plugging it into the equation. There's my mgh. G I know is 9.8 here at sea level on Earth, and that's how I came up with 2,450 joules. How did you do? Well, hopefully it worked out for you. I know these things can be confusing, but if you have some questions, bring them to class with you next time, and we'll talk about them. Okay, so what is energy, right? What is energy? Well, I told you that energy is the ability to do work. So, give an example of work being done. Think of an example of work being done. Maybe lifting this coffee mug would be an example of work being done, right? Well, any kind of work that you do, there's going to be some energy involved. So where did that energy come from to do that work? Well, think about it, right? Probably you would say maybe the food I ate, right? Well, how about the food I ate? Maybe I had a Chicken sandwich. I don't know. But what I guess the point I'm trying to make here is how about this transfer of energy? Where would the chicken sandwich have gotten its energy? Well, from the chicken, I guess, originally. And the chicken would have had to eat some kind of food as well. And that food would have been something that was grown in the ground, probably some kind of grain. And that energy could be traced back to the sun. So every amount of work that you see any person doing, work from the physics standpoint of view, the energy for that can be traced back to the sun. The sun is our source for all the energy done. And really, even our cars moving down the road, right? Fossil fuels were originally things that were relying on the sun. So the sun, pretty important to us. We like you, sun. You're looking good there with those sunglasses. That's kind of odd, right? The sun wearing sunglasses. Anyway, let's see what else we got going on here. Here's some concepts, and like momentum, we had the idea that momentum would be conserved. That was the last topic that we had done, or a recent topic. But energy cannot be created or destroyed. That's an interesting concept because that means that all the energy that we ever had at the beginning of the universe, theoretically, is the energy that's available to us now. There's no new energy. Now, of course, it can go from one form to another. We know that, right? And this idea here is the conservation of energy. And that's a very simplified version of talking about it. But we can change energy from one form to another. Conservation of energy is what we're talking about. So for our purposes, we're going to talk about the conservation of mechanical energy, and we'll limit our discussion to that, at least as far as our calculations. We'll talk about some things in class, but let's see what we have here. Here's an example. We have a 20-kilogram snowboarder, and they're at rest at the top of a hill. They're getting ready to go. So what is their potential energy? All right, well, fair enough. We've done some problems like this already. So give it a try. See what you come up with, and when you come back, I'll give you the answer and my solution. Hey, welcome back again. All right, I got 2,940 joules for being at the top of the hill. How about the kinetic energy? Well, they're at rest, so their kinetic energy is 0. And how about their total energy? Their total energy is also 2,940 joules. All right, now hold on a minute here. That could be a little bit confusing. Let me try to clarify these answers for you and show you how I figured that out. Well, first of all, identifying the information is our regular starting point. And that means we could figure out the potential energy by plugging in mg, the 9.8, and the height 15 meters. That's how I got the 2,940 joules. Because the speed is 0 and kinetic energy involves speed, then the kinetic energy is 0 joules. But here's the idea of the conservation of energy for mechanical energy as we'll apply it to our class. But take a little note of this one here because this will keep coming up. The idea is that the total energy for our purposes will be the potential energy plus the kinetic energy. Certainly, there are more types of energy out there. But for our purposes, we're going to do this, we're going to look at it this way, which is a little bit of a simplifying assumption. But that means the total energy is 2,940 joules. Now, think about this for a minute, because this is an important concept. We're going to now look at the snowboarder as they go down the hill. But a key point is that the total energy won't change. It's a simplifying assumption. In real life, it might. We might lose some to friction. We're going to assume that the total energy stays at 2,940, that the potential energy and the kinetic energy will always add up for this problem to 2,940. Let's take a look at this. All right, so now I've got the snowboarder, the same snowboarder, but they are starting to come down the hill, right? Starting to come down the hill, so now they are no longer 15 meters above the ground, they are 10 meters above the ground. So I'm going to ask these same kind of questions, but I'm going to add in an extra one. What is their speed? Once you have kinetic energy, you can have speed. All right, well, you can give that a try if you like. And when you come back, I'll have the answers for you. Okay, welcome back. Here are my answers. Now, you might be a little confused at this point. So let me break down how I got all 4 of these answers. First of all, I'm going to identify the information. There's my 20-kilogram snowboarder but now they're at a height of 10 meters. But I've added in the total energy at 2940 because for this snowboarder on this hill, for this problem or set of problems, the total energy stays the same. Remember, we had gotten 2940 earlier. We're still going to use the 2940. The potential energy has changed, right? It's not 2940 anymore because they're farther down the hill. So here's the potential energy, the mass, the 9.8, the 10 meters above, and that means there's 1960 joules worth of potential energy. Okay, now remember, the total energy is still 2940, and total energy for our purposes is going to be the potential energy plus the kinetic energy. So I can backtrack now to figure out the kinetic energy. I know the total energy, 2940. Potential energy is now 1960. Whatever's left over here, or the kinetic energy had to pick up where the potential energy dropped. So by subtracting off the 1960, I can see that my kinetic energy is 980 joules. That's a little confusing perhaps. If it is, bring your questions back to class, and we'll see what sense we can make out of it. But now that we have the kinetic energy, we can figure out the speed. The kinetic energy we know the mass is 20, and we can figure out the speed. So here I have taken 1/2 of the mass, 1/2 of 20 is 10. I divided the 980 by 10 to get v squared by itself. That gave me 98, and I'm taking the square root of that, and that's how I came up with the speed at 9.9 meters per second. So there you go. Those are my solutions. I wonder how you did. I'm sure you'll give me some feedback when we're back in class. But we're going to look at this one more time. We're going to look at the same snowboarder one more time. Let's say they have reached the ground. Now I know you say when they reach the ground their speed is 0, but not really, not until they stop themselves. So I'm talking about just as they got off the hill, assuming that the only thing that we're dealing with is kinetic and potential energy. Well, let's take a look at that and see what we got. All right, so, well, there's a snowboarder. All right, so here are the answers I got, but let me also show you my work for that. Or actually, why don't you see if your answers and mine are the same, and then come back and I'll show you the work. That's even better. Give it a try yourself. All right. How did you do? Did you get these answers? Well, let's see what we got here. We are now the same 20 kilograms. Remember, the total energy never changes, so there's the 2940. Now the height off the ground is 0 meters. So the potential energy is also 0, right? Because height 0 means I have 0 potential energy. All right, now let's figure out the kinetic energy, right? You probably can see this coming already. Total energy is the potential energy plus the kinetic energy. So the total energy is now all kinetic energy, right? Kinetic energy is 2940 because the potential energy is 0. And then, just like we did before, we can solve for the speed, and it makes sense that the speed is getting faster and faster. So here's the kinetic energy, the 2940, 1/2 of 20 is 10. I divide that off, and I take the square root, 17.15 meters per second. Well, I hope this video was useful. I do want to thank you for watching, and I'll see you back in class.
Well, we gonna rock to the rhythm and the blues.